Section 2.3, heat. Heat always flows from a higher temperature object to a lower temperature object, or from a higher temperature region to a lower temperature region. Heat is also transitory, just like work. Heat is not associated with the state of the system. It's the change between two different states. So given the initial state of a system and its final state, there is still no way to compute heat. We have to know more information about the entire process or the path that connects the initial and final states. So let's work on a few example problems. We're going to calculate the amount of heat involved in the following isothermal processes. First, I want to remind you, we will be looking at ideal gases. The attraction between ideal gas atoms is zero. The repulsion is zero. Therefore, the potential energy of an ideal gas is always zero. So there's no change in the potential energy of an ideal gas, no matter how you deal with this gas, no matter how the state of the system changes. Again, this is because the attraction, repulsion, and the sum of attraction and repulsion is always zero for an ideal gas. Therefore, the internal energy of an ideal gas only depends on its kinetic energy. And remember, temperature is the measure of kinetic energy. Therefore, higher temperature, higher kinetic energy. Lower temperature, lower kinetic energy. What if the temperature remains unchanged? Well, very simple. That means the internal energy of the ideal gas remains unchanged. Therefore, the change of the internal energy is zero for an ideal gas that undergoes isothermal process. In summary, for ideal gas, the change of potential energy is always zero. The kinetic energy change is also zero if the temperature changes zero. And therefore, the internal energy change of an ideal gas in a isothermal process is always zero. There's no change. Alright, so that means delta U is zero. That means Q is negative W. Right? Remember, delta U is equal to Q plus W. So in this kind of situation, we usually compute work first, and then we compute Q. So 20 liters of ideal gas expands to 80 liters against P external is 1 bar. W is negative 60 bar liters. Well, how do you compute this? It's just negative integral of P external dV. We know what the P external is. We know the change of volume. Then we can compute work. So Q is negative W in this case. Q is 60 bar liters. Process B, two-step expansion. A 20-liter ideal gas expands to 40 liters against 2 bar external pressure, and then it expands to 80 liters against 1 bar external pressure. So it's a two-step process. You need to compute the work for step 1, that's negative 40, and then step 2, that's also negative 40. In sum, you get negative 80 bar liters. What about Q? Q is delta U minus W. Again, delta U is 0 because, again, delta PE is 0. Delta KE, kinetic energy change, is also 0. So the result is Q is equal to 80 bar liters. Now, finally, the third process. What if this system, this ideal gas, expands against this external pressure? It's not a constant, but we know P external is equal to the system pressure P. And then what we do is, again, we compute work by replacing external pressure with P. And PV equals nRT, therefore the result is negative 111 bar liters. That's for work. What about Q? Q is delta U minus W. Again, we have Q plus W equals 0.